Welcome viewers. Today we are going to discuss rank of a matrix. The preliminary concepts which is required for rank of a matrix is the determinants and the submatrices. So, let us have an m by n matrix A, then R will be its rank if this matrix has at least one submatrix of order R which is non-singular, but all submatrices of order greater than R are singular. Now, to illustrate this definition, I will take an example. I have a 3 by 2 matrix, that means 3 rows and 2 columns, and the rank of this matrix is to be obtained. To find out the rank, I will first consider all submatrices of order 2. Matrices of order 3 are not possible for this matrix. So, I will start with submatrices of order 2. This matrix will have 3 submatrices of order 2, that is 1, 2, 3, 6, that is the first determinant corresponding to this. The second determinant is corresponding to the submatrix consisting of first row and the third row, and the third determinant will be second row 3, 6 and 4, 8. If you compute the determinant of these matrices, one can notice that this determinant is 0, 1 into 6 minus 2 into 3 0. This determinant is also 0, 1 8 minus 8 is equal to 24 minus 24. So, determinant of all these sub matrices, they are 0. So, the determinant this matrix cannot have rank 2. So, let us see what is the rank of this matrix. So, we will consider submatrix of order 1. So, this matrix will have 6 submatrices of order 1, that is the element itself 1, 2, 3, 6, 4 and 8, and their determinants are non-zero. So, we have a determinant of order 1 which is non-zero, and all determinants of order 2 bigger than 1, they are 0. So, we can say rank of this matrix cannot be 2, but rank comes out to be 1. So, that is how we define rank of a matrix. Now, one can observe that for a matrix which is of order m by n, then rank A is minimum of m and n, because we have to obtain submatrices which are square matrices. So, the minimum of this will be the rank. For n by n square matrix A, rank A is less than equal to n. Rank cannot be bigger than that. So, we say for a square matrix, rank A will be less than equal to n. If rank of A is less than n, that clearly means that determinant A is 0. This is coming from the very definition of rank, and that means A is singular. On the other hand, if rank A is equal to n, then determinant has to be non-zero. Again, this is from the definition, and this will be now become the definition for non-singular matrix A. So, we say A is non-singular if its determinant is non-zero. Further, one can observe that rank of 0 matrix is 0, because in that case all determinants of order 1, they will be 0. So, the rank of 0 matrix is 0. Now, we have a result which says that if determinant A is equal to 0, then determinant B is 0 when B is obtained from A by elementary linear transformations. This result we have established in my earlier lectures. To prove this, let us say B is equivalent to A. Why? Because B is obtained by applying elementary linear transformations to A. That means there exists non-singular transformation P and Q, so that B is equal to P A Q. Further, it has been given that determinant A is equal to 0. We have to prove that determinant B is also 0. So, to do this, we can find out the determinant of this. So, determinant D on the left hand side is equal to determinant of PAQ, which can be written as determinant of P into determinant of A and determinant of Q, but because they are obtained, they are the elementary linear transformation matrices, determinant P and determinant Q. So, they cannot be, their determinant cannot be 0, they have to be non-singular. So, determinant P is not 0, determinant Q is not 0, and what are these determinants? They are simply numbers. So, product of 3 numbers is 0 if one of them has to be 0. So, determinant D is equal to determinant P into determinant A, determinant Q. Determinant Q is not 0, determinant P is not 0. So, we have only one alternative, that is determinant A is equal, that is determinant B is equal to 0. So, product of this means that determinant B is equal to 0 when determinant A is equal to 0. So, whenever a matrix is obtained, whenever we apply linear elementary transformation, then the obtained matrix will have determinant 0 if the original matrix also has a determinant 0. So, that is the result, and since rank and determinants are related, so we can say that on the basis of this result that rank of equivalent matrices are same. So, if determinant A is equal to 0, then after applying linear transformation determinant B is also 0. If it is non-zero, then this also be non-zero. So, rank of equivalent matrices are same. Further, rank of A and rank of its transpose, they are equal, because rows and columns can be the determinant will not be affected by changing the transpose. So, if determinant is not 0, then determinant of A transpose will also be not 0, and that is why rank of A is equal to rank of A transpose. Now, I will try to define rank of a matrix in slightly different manner. Now, this will do in the same manner as we have done for linear transformation. So, I want to relate the two concepts. So, let us have a matrix A, which is an m by n matrix, and let us now have a linear transformation T, which is from Rn into Rm. We say that each column is a vector in Rm. If this is a linear transformation, that each column in A is a vector in Rm, then n columns of the matrix, because it is an m by n matrix, it has n columns, then the n columns of the matrix constitute column vectors of A in Rm. The idea is this matrix being m by n matrix, it will have n column vectors in Rm. Then the subspace spanned by these n column vectors of the matrix is called column space of A. This we have proved that if A represents the matrix of linear transformation, then that will be a vector space. So, we call that vector space as a column space. So, the subspace spanned by n column vectors of the matrix is called column space of A. The column space is a subspace of Rm, this we have already established. The dimension of column space is called the column rank of A. So, the number of linearly independent column vectors is the column rank of A. Similarly, we define row rank. So, each row of the matrix is a vector in Rn for the given transformation. Then the m rows of the matrix A, which is m by n, constitute m rows of vector A in Rn, and that means if A is m by n matrix, then the subspace spanned by these m row vectors of the matrix is called the row space of A, and the row space is a subspace of Rn, this we have proved earlier. And finally, the dimension of row space is called the row rank of A. So, we have a matrix A, column vectors constitute the column space, and it will have a row rank, the number of linearly independent vectors, linearly independent column vectors, and it will have a row space generated by the the row vectors of the matrix, and the row rank is the number of linearly independent vectors, linearly independent row vectors in A. Now, on the basis of this, let us find the basis for column space of this matrix. So, I am just trying to illustrate what I have just described. So, we have a matrix, it has 4 rows and 3 columns. So, we have to find out the basis for the column space. Now, this has 3 column vectors, first vector is 1, 2, 1, 1, minus 2, minus 1. Second one is 2, minus 1, minus 1, 4, minus 3, 3, 3 and minus 2. This will generate a vector space. So, what will be its basis? So, let us find out the basis for this matrix. So, we have these 4 column vectors. I am denoting these column vectors in this particular manner. This is just to save space. So, 1, 1, minus 2, minus 1, they are not written vertically, but they are written horizontally, and this represents that it is the transpose. So, this row vector transpose will make it a column vector. So, we have 3 column vectors as I have illustrated. Now, we have to find out its basis. So, we say column vectors generate a subspace S in R4, it is M is 4. So, it will generate a subspace S in R4. So, what we have to do is we have to find out the independent column vectors that will constitute basis for S. For this purpose, let us assume 3 constants C1, C2, C3 such that C1 first vector plus C2 multiplied by the second vector plus C3 multiplied by third vector is 0. That means, the linear combination of these 3 vectors is 0. So, let us try to find out the solution of this equation. So, this equation actually gives us 4 equations. So, if we compare the first element from this, so it is C1 plus twice C2 minus 3 times C3, that is the first equation. The second equation is C1 minus C2 and plus 3 C3, that is the second equation. So, this way we form 4 equations. Now, these 4 equations have to be solved for C1, C2 and C3. So, if we add first 2 equations 1 and 2, then this will be simply 2 C1 plus C2, this will cancel out, is equal to 0, and this means C2 is equal to minus 2 times C1. Similarly, if we when we substitute this solution in 3, this equation 3 will have C2 is equal to minus 2 C1. So, this will get cancelled with this. What we have is simply C3 is equal to 0. So, this is what we obtained from the third equation, and equation 4 gives, if you substitute in 4, C3 is equal to 0, this will give me minus C1 plus 4 C2 is equal to 0, and if I substitute this here, it is minus C1 minus 8 C1 is equal to 0, that gives me C1 is equal to 0. So, C1 is equal to 0, C2 is equal to 0, C3 equal to 0. So, this system will have a 0 solution. So, what we have obtained is we have a linear combination equal to 0, and this is possible only when C1, C2 and C3 are constants, and that means these 3 vectors are linearly independent. That means they will have the column rank as 3. So, the given matrix has column rank 3. Then the next results relates the matrices A and B, which are row equivalent matrices. Then the row space of A and B are identical. That is, if we have 2 matrices A and B which are of same order and they are row equivalent matrices, then their row space, they are identical, because they are let us try to prove this. Let B is row equivalent to A, that has been given to us. The matrix B can be obtained by applying a finite sequence of elementary row operations on A. That is the meaning of A equivalent to B, or A and B are two equivalent matrices. So, the matrix B can be obtained by applying a finite sequence of elementary row operations on A. Then row vectors of B are linear combination of row vectors of A. Then row space of B is contained in row space of A. Now, if they are linear combinations, that means the determinants will be, if one determinant of B is equal to 0, a submatrix of B having determinant 0, then the same will happen to the other matrix also, and that is why their ranks will be same. And ranks will be same, that means their row spaces will be identical. So, row vectors of B are linear combination of row vectors of A, and row space of B is contained in row space of A. Now, we say that row space of A is contained in row space of B. Same way we can prove this, the way we have done for the other part, and since A is contained in B and B is contained in A, so row space of A and B are identical. So, that is the result. Row space of matrix A and its equivalent reduced row echelon form are identical. So, I have started with any matrix B, but then we can apply it for equivalent reduced row echelon form, and this result is important because with the help of this result we can solve system of equations, and we can easily find out the rank of equivalent reduced row echelon matrix. So, to find out the rank of a matrix A, we can find out the rank of a equivalent row reduced echelon form, and we can say that whatever be the rank of equivalent reduced row echelon form, the same rank will be there for the matrix A, and finding rank of this form will be simpler than finding rank of this matrix, and that is why we try to reduce matrix A into this form, find out the rank of this, and then we say the same will be the rank of A. So, this gives us a procedure for finding row space of a matrix A. Now, it says that the non-zero rows of reduced row echelon form B of a matrix A constitute the basis of a row space of the equivalent matrix A. In the echelon form, we will see how many rows are non-zero, and that will the non-zero rows will actually constitute the rank of the matrix, that will form a basis, and that will give us the rank of the matrix. So, this, as I told you, this result gives us a procedure for finding the basis of the subspace S of Rn spanned by the given set of vectors u1, u2, un. Now, the procedure is, step 1 is form the matrix A of given m rows and n columns such that the ith row of the matrix is the row vector ui. That is the first step. The second step is transform A to reduced row equivalent form B. Once we have done this, the third step is the non-zero rows of B form basis for the subspace. So, I have first established this procedure, and now after stating this procedure, I will illustrate this with the help of an example. So, we have been given 4 vectors in R5. We have to find the basis of subspace of R5 spanned by these set of vectors. So, V1 is 1 5 7 6 0, V2 2 4 8 5 1, V3 is 3 1 7 5 minus 1, and while V4 is minus 1 2 0 4 and minus 3. So, according to the first step, the first vector is written as a row vector of the matrix A, the second vector is written as the second row of the matrix, third vector forms the third row of the matrix, and fourth vector forms the fourth row of the matrix. That means, from these given vectors, I will form the matrix A, where these vectors are its rows. Once we have obtained this matrix A, we apply a linear elementary transformation, so that this matrix will be reduced to reduced row echelon form, and then we will see how to form its determinant. So, first we apply linear transformations to reduce it into reduced row echelon form. So, I will give you a sequence of steps to reduce the given matrix A into row echelon form. So, I have the first row written as it is, and I will first try to make the first columns 0. So, when I apply linear transformation, then the matrix A will reduce to this form, and from this we apply more linear transformations. So, that this will further reduce to this form, and then from here we will come to this form. Again apply a linear transformation, suitable linear transformation, then we will have this matrix. Now, you can notice that this matrix has these, the bottom row as 0. We further apply a linear transformation to check whether this row or any other row can become 0. So, we apply these transformations. So, this matrix reduces to this. Now, this is the final form. If I try to apply more transformations, then either this will be 0 or this will be 0. So, I can stop here. So, we can divide this matrix into 4 different parts. One part is this, another part is this, third part is this, all zeros, and we have a 0. Now, in this we can say that this is the echelon form. We will have 1 here, 1 here, and this is 1. So, we have this is 0 and this is echelon form, and from here one can notice that there are 3 rows which are non-zero. So, the dimension of row space is 3. So, we have obtained that the dimension of this matrix, its row space is 3, not 4, but what are the basis vectors that is to be obtained. Now, the first vector, this is the first vector, it has 1 here. So, first vector is the 1 0 2 0 1, 1 0 2 0 1. This is the element of the basis vector of given row space. Then this vector 0 1 1 0 1, this also is a basis, this constitutes the basis, and the third vector will be 0 0 0 1 and minus 1. So, the given matrix A will generate a row space, and the basis for the row space is determined as this. So, these are 3 vectors which are linearly independent and they will generate the row space. Now, this theorem says that the row rank and column rank of m by n matrices are identical. Now, to prove this, let us consider W1, W2, Wn denote the columns of A. To check the independence of these vectors, we consider the linear combination of these vectors C1 W1 plus C2 W2 plus Cn Wn is equal to 0. Now, the solution of this homogeneous system, it is a homogeneous system, and this can be obtained from the augmented matrix A0. This method we have already discussed. So, I will just apply this method to solve this system, because to establish the linear independence of these vectors, I have to find out the constant C1, C2, Cn. If all these constants come out to be 0, then these vectors W1, W2, Wn will be linearly independent, otherwise they will be dependent. So, I have to solve this, and this is the method which I apply. So, let us consider. Now, we try to transform the matrix into reduced row echelon form. Before I proceed further, I like to introduce the meaning of reduced row echelon form, although we have done it earlier, but for the sake of the viewers, I will just define what do we mean by echelon form. So, this particular matrix is in reduced row echelon form, because the once they appear in this matrix, they actually form an echelon, a staircase pattern is obtained. That is why we call it an echelon form. We call it reduced row echelon form because every row will have a leading one. This row has a leading one, this row has a leading one, and the third row has leading one. The leading one means if this particular row is having leading one, then all other elements in this column will be 0. So, this is leading one, all other elements are 0. So, in this case this is 0 and we have this. So, we try to reduce the given matrix in this particular form. Now, this matrix has some number of rows as 0 and rest of the rows will have this pattern. So, non-zero elements in this matrix will have this staircase pattern. Once we have obtained row echelon form, we try to find out the independent column vectors of this equivalent matrix. These are those column vectors of A which corresponds to the columns of leading ones. That means, if this is the echelon form, then this column corresponding to this leading one row and this column in which we have this leading one and this column. So, this vector and this vector, they are linearly independent vectors. All this vector and this vector, they are linear combinations. So, we have only this vector, this vector and this vector which are linearly independent. So, we have 3 rows, 3 leading ones. So, 3 vectors will form the set of linearly independent vectors, and that is why we say row rank and column rank are equal. So, the rank of column space is the number of leading ones or the number of non-zero rows, and this proves that row rank is equal to column rank. Now, in this example, we try to find a basis for the column space of the matrices. So, in earlier example, we have obtained basis for the row space. Now, we try to find the basis for the column space of the given matrix A as this. Now, given this matrix A, the column vectors 1 1 minus 2 1, 2 minus 1 minus 1 4, minus 3 3 3 and minus 2, they are arranged, they are considered, and let we have C1 C2 C3 arbitrary constants.
Start.
This linear combination C1 first vector plus C2 second vector plus C3 third vector is equal to 0. Now, this system can be written in the form as this matrix, and from here we can obtain the augmented matrix as this. Now, we try to reduce this augmented matrix into row reduced echelon form. So, we start with A0, which is this given matrix. We apply linear transformations. First, we try to make this element simplified. This is 0. So, we have this reduced form. Further, when we apply more linear transformations, then from here we can go to this matrix, from here we can go to this matrix, and finally, we will have this matrix. So, we have now B matrix, and this B matrix consisting of these identity matrix and these elements. So, we have now row reduced form as this consisting of 3 rows, and these are the column vectors, and these are the leading rows with leading elements. So, this vector and this vector, they constitute the basis. So, B is reduced row echelon form which does not have any 0 row, and that means the column rank is 3.
Start.
Now, we discuss null space of a matrix. So, first we will define what do you mean by null space of a matrix. It is defined as a space spanned by the solution vectors of the system Ax is equal to 0. So, if A is an m by n matrix, then nullity of A is defined as the dimensions of the null space. Now, on the basis of this, we can say that if A is an m by n matrix, then rank A plus nullity A is equal to n. Actually, this result we have already established when we have a linear transformation T. But now we have since we have already established the association between the linear transformation T and the matrix A, we have similar result for the matrix A. But only difference is that A is an n by n matrix. So, if we have an n by n matrix, then rank A plus nullity A is equal to n. Now, to prove this, we start with the augmented matrix A0 and we transform it to reduced row echelon form B0 having R non-zero rows. Then by definition of the rank, we say the matrix will be having rank R. So, we have a matrix A when it is transformed to echelon form consisting of R rows, then it will look like as this matrix. So, transformed matrix B will look like as this. One can notice that this matrix has 4 parts. We have R rows here which are non-zero, we have m minus R rows which are 0, then these are 2 parts and the other 2 parts are this. So, this is the identity matrix here, we have null matrix here and null matrices here. So, the given matrix A is transformed to this matrix B. So, this is identity matrix having of order R. So, we say that this is how we have divided. Then we say that the solution space of Ax is equal to 0 will have dimension n minus R, because the vectors will be represented in terms of these n minus R vectors. So, the dimension of null space is n minus R, and then rank A plus nullity A is equal to n. Rank A is R, nullity A is n minus R. So, this is equal to n. So, we have defined rank of a matrix A, the nullity of A, and then we have established rank A plus nullity A is equal to n. Now, we will illustrate these concepts with the help of an example. So, let us have a 3 by 3 matrix A as this matrix. Then we have to find the rank and nullity of this matrix. So, I will start with the matrix A and try to reduce it into row echelon form. So, it is 1 minus 1 2, 0 minus 1 1, 2 1 and 1. I try to make this 0. So, this matrix is transformed to this, and by applying suitable linear transformations, then elementary transformation when applied to this will reduce this matrix to this, and further this will be reduced to this, and from here we will go to this matrix. Now, one can notice that this is reduced to row echelon form like this. This has leading row, this is another leading row, and this third row is 0. So, we have echelon form, this is IR, that is I2 in this case, and this is 1 minus 1, they are non-zero here, and then we have a 0 row, and that means the rank of A is equal to 2. That means what we have done is this, you can very easily see that we have a second order determinant which is non-zero, and third order determinant will be 0 because of this 0 row. So, rank of this matrix is 2. Now, to find the nullity, we have to solve this Ax is equal to 0. So, what are the solutions for Ax is equal to 0? So, what we can say is this equation will not contribute anything because this is identically satisfied. So, this row will not contribute towards the solution. So, we will have only this and this row. So, we will have x plus z is equal to 0 and y minus z equal to 0, and this gives me x is equal to minus z and y is equal to z, where x, y, z, these are the elements of this column vector x. So, x is equal to minus z and y is equal to z. That means, we can write down the first vector in first component in terms of third and second component in terms of third, and we can assign any value to the third component z. So, every solution of the homogeneous system A x is equal to 0 is of this form. So, you change the value k and you will be having this k and minus k, the second component and the first component. So, we say the solution of this equation will be of this form. So, this will be the null space. So, the basis for null space is this. Every vector which is a solution of this will be generated by this vector. So, this forms a basis for null space, and since basis constitute of one vector, that is why we say nullity is 1. And for this example, we have rank is equal to 2, nullity is equal to 1, and the order of the matrix is n by n or 3 by 3. So, 2 plus 1 is equal to 3. Now, the rank of a square matrix can be used to determine whether the given matrix is singular or non-singular. If nullity is equal to, if suppose in some example nullity of A comes out to be 0, the rank will be equal to the size of this matrix A. So, we can use this result to know whether a given matrix is a singular matrix or a non-singular matrix. Now, we will establish certain properties of rank. So, first property is, if a non-singular matrices P and Q are given, then rank of P A is equal to rank of A Q and is equal to rank of P A Q is equal to rank of A. So, rank, this matrix A is being given to us, P is non-singular. So, P into A will have the same rank as rank of A. Similarly, Q, for the given matrix Q, rank of AQ will be the same as rank of A. Also, rank of PAQ is equal to rank of A. Further, two matrices A and B are equivalent if and only if rank A is equal to rank B. So, proof is simple. We first assume that A and B are equivalent, and that means there exist non-singular transformations P and Q. So, that we can write down B as P A Q. That means there are some elementary transformations which can be applied to A, that will give me B, and similarly we have some linear transformation, set of linear transformations, so that we can have B is equal to P A Q. So, the two matrices are equivalent if B is equal to P A Q, P and Q are non-singular, then rank of A is equal to rank of B, because P and Q are non-singular. Otherwise, if rank of A is equal to rank of B is equal to R, then rank of P A Q, the two matrices will be similar. So, let us try to do this. Let us say rank of A is equal to rank of B is equal to R. That means, you can apply linear transformations to the matrix A, so that it can be reduced to row echelon form, and since its rank is equal to R, this matrix will be obtained as this. And rank B is also R, so this can also be reduced by a series of linear transformations. So, B will be equivalent to this row reduced echelon form. So, when you apply linear transformations to B, it will be reduced to P1 BQ1 form, and when you apply linear transformations to A, it will be reduced to PAQ, and since both of them are equal, so rank is R. So, if we can say PAQ is equal to P1 BQ1, so A and B are equivalent. Now, the next property suggests that rank of AB, the product of two matrices, is less than equal to rank minimum of rank of A and rank of B. This is an important property. So, to prove this, let rank of A, which is an M by P matrix, is R. then rank of AB is equal to rank of A matrix is written as P and Q, where N is the echelon form. So, after applying linear transformation, A can be reduced to P and Q. So, A can be written as P and Q. So, I am substituting P and Q for A. So, rank of P and Q into B is equal to rank of NQB, because P is a non-singular transformation, P and Q are non-singular transformation. So, that will not affect. So, that is why rank of AB is equal to rank of NQB, and rank NQB, now rank of AB is less than or equal to rank of P, and from here rank of AB is less than or equal to rank of A. Similarly, one can prove this, and now we can combine these two results, and that result gives me that rank of AB is less than or equal to minimum of rank of A and minimum of rank of B. Now, we have an important result. It says that if n by n is a non-singular matrix, then rank of A is equal to n. So, if n by n is a non-singular matrix, this is possible if and only if rank of A is equal to n. So, this has two parts. Again, if rank of A is equal to n, we have to prove that it is non-singular, and if it is non-singular, then rank of A is equal to n. So, we start with the first part. If rank of A is equal to n, that means there exists number of non-zero rows in A in this augmented matrix is equal to n. That is how we have defined the rank of A. So, the number of non-zero rows in this matrix is equal to n, then A is in. So, we can reduce this matrix into echelon form. So, A will be in, that is the meaning of rank of A is equal to n, and if A is equal to in, then its determinant is not 0. So, A is going to be non-singular. So, if we start with rank is equal to A, rank of A is equal to n, then A is non-singular. In the second part, we have to prove that if A is non-singular, then rank of A will be n. So, to prove this, since A is non-singular, so A is row equivalent to in, and since A is row equivalent to in, A has no non-zero rows. A is n by n matrix and its row equivalent to in, so it does not have any non-zero row, and that means rank of A is equal to n.
Start.
Now we will try to relate linear systems, non-singularity and rank of a square matrix. So, if we consider a homogeneous system of n linear equations in n unknowns, then we can write down this system in the form Ax is equal to 0, where A is an n by n matrix and x is a column vector in Rn, and this is identity in Rn. Then the system has a non-trivial solution if and only if A is singular. So, this system will have a 0 solution, because when x is equal to 0, A0 is equal to 0. But the problem is when this will have a non-trivial solution. So, we say the system will have a non-trivial solution if and only if A is equal to A is singular, or determinant A is equal to 0. So, to prove this, we first assume that the non-trivial solution is possible for this system and A is singular, and since A is singular, so A is invertible. Since A is invertible, so we can write down, we can multiply it by A inverse. So, A inverse Ax is equal to 0, A inverse Ax is equal to 0, and A inverse A is identity. So, Ix is equal to x, so x is equal to 0. So, we have started with a non-trivial solution, we have assumed that A is non-singular, but we finally arrive at a contradiction that x is equal to 0, and that means our assumption that A is non-singular is not correct, and that means it is non-singular. Now, in the second part, we say A is singular. If A is singular, that means this augmented matrix will have a 0 row. and if it has a 0 row, then rank of A is less than n, and this implies the nullity of A is not 0, it will be 1, and that means the system will have a solution other than 0. That is the basic definition of nullity, will have a solution which is 0. So, since nullity of A is not 0, so we will have a solution which is non-zero, but Ax is equal to 0. So, the system will have a solution other than 0, and that means a non-trivial solution is possible, and that proves that the system has a non-trivial solution if and only if rank A is less than n, and the linear homogeneous system of m equations in n unknowns when m is less than n will always have a non-trivial solution. So, the next thing is we consider a non-homogeneous system of m equations in n unknowns. So, we have written the system in the form Ax is equal to b, where A is an m by n matrix, m equations in n unknowns. That is why A is m by n and B is a column vector. This system will have a solution if and only if rank of A is equal to rank of augmented matrix A B. Now, if such a thing will happen, then we say the system is consistent. If it is not, then system is not consistent. If rank of A is equal to n, then the system has a unique solution, and if rank A is less than n, the system has infinitely many solutions. Now, let us see this augmented matrix AB. This can be written as IR A B dash 0 0 B double dash. That means you can transform this matrix by using elementary transformation into this form. So, R being the rank of this matrix, these are 0 rows. Now, here if B double dash, if rank A is equal to rank of AB, if that is possible, if rank of AB, if rank of A is equal to rank of AB, that means B double dash is equal to 0. If B double dash is not 0, then this is not possible. And if B double dash is 0, then they are consistent, this is solution is possible. If B double dash is not 0, then this condition will not be satisfied, and that means 0 is equal to some non-zero value on this side. So, that is not feasible, and that is why the system will be inconsistent. Now, rank A is equal to n, then the inverse is possible, and when the inverse is possible, then we can have a unique solution. And when rank A is less than n, then we will have infinitely many solutions for the given system. Now, let us illustrate this with the help of an example. I have been given a set of a system of equations, 3 equations in 3 unknowns x, y and z. You have to find out the values of A and B for which this system has no solution, have a unique solution or an infinitely many solutions. So, we will use the results which we have discussed just now one by one. So, to start with, I will consider the augmented matrix 2 3 5 3 3 7 2 3 A, that is the coefficient matrix, and the matrix B is 1 3 B. I try to apply linear transformations and reduce this matrix into this form. So, what I have done is I have subtracted this element, this row from this. So, this is the linear operation I am applying. 3 minus 2 is 1, 3 minus 3 is 0, 7 minus 5 is 2, 3 minus 1 is 2, and I am subtracting third row from the first row, that gives me 0 0, A minus 5 and B minus 1. So, if I start with this and apply linear transformations again, then this can be reduced in this form. So, what I have done is I have divided the second row by 3. So, it is 0 1 1 by 3 and minus 1, and 0 0 A minus 5 and B minus 1. Further, if I subtract 3 times this row, then this becomes 2 minus 0, 0, this becomes 0, 3 minus 3 is 0, and this becomes 4, and this element becomes 4, and then one can notice that this, you can divide this by 1, so this will become an identity matrix, and if A is equal to 5, so this row will be 0, and if B is not 1, then 0, the system will be, this system is actually equivalent to Z into 0 is equal to B minus 1. B minus 1 is not 0. So, this equation does not have any meaning, and that is why this will not have any solution. So, if A is not equal to 5 and B is not equal to 1, that is A is not 5, let us call it C, and B not equal to 1 is D, then rank of A is equal to 3, because C is not 0. So, rank of this matrix is 3, and rank of this matrix, if D is not 0, will also be 3. So, whether it is 0 or not, this rank will be 3. So, rank of A is equal to rank of the augmented matrix. So, the number of equations are 3. So, this is a consistent system, and this also have a unique solution, because this is also rank A is equal to rank of AB is equal to the number of equations. So, this system will have a unique solution. But if A is equal to 5 and B is not equal to 1,
Start.
Now in the second case we say that A is equal to 5 and D is equal to B minus 1 is not 0. So, in that case the augmented matrix will become as this, and you may notice that the last line has zeros here and D here. So, that means that rank of A matrix is cannot be 3, because this row is going to be 0, but there exists a matrix having rank non-zero. So, the augmented matrix, the augmented matrix may have rank 3, but the matrix A has rank 2. So, this system is not consistent. Rank of A is equal to 2, rank of its augmented matrix is 3, and the number of equations are given to be 3. So, this has an inconsistent system, and it has no solution, because Z into 0 is equal to D is not possible. So, we have an inconsistent system in this case. So, we can get this by simply checking the rank of A and rank of its augmented matrix. If they do not match, the system will be inconsistent and no solution will be possible in that case. Now, in the third case, if I consider C is equal to A minus 5, which is not 0, and B is equal to 1, then the augmented matrix will look like as this. Now, in the third row we will have C, which is not 0, and that means that this 3 by 3 matrix A, it has determinant non-zero, or rank of the matrix A is 3, and rank of A colon B, that is the augmented matrix, will also be 3, because this is 4 by 4 matrix is not, 4 by 4 determinant is not possible. At the most rank will be 3 in this case. So, rank of augmented matrix is also 3, and this is what I have. Rank of A is equal to 3, rank of A colon B is equal to 3, and the number of equations, they are 3. So, this will have a unique solution. The only difference is that here this Z is going to be 0, because this equation is actually equivalent to Z into C equal to 0, but we have a unique solution in this case. And the last case is when A is equal to 5 and B is equal to 1, and if this happens, then our augmented matrix will look like as this. Now, what will happen? This is the coefficient matrix. This coefficient matrix has a row equal to 0. That means the rank cannot be 3 because this determinant will be 0, rank cannot be 3. And if you consider this is to be 0, then this augmented matrix also will not have rank equal to 3. So, the rank of augmented matrix will also be less than 3. Now, let us see what is the rank of the coefficient matrix. It is not 3, that is clear, but this matrix has determinant non-zero. So, the rank of this matrix is, this coefficient matrix will be 2, and similarly if you consider this complete matrix, then the rank of this augmented matrix will also be 2. So, rank of A is equal to 2, rank of A colon B equal to 2. That means this system may have a solution. It is not inconsistent, it is a consistent system, it will have a solution, but since the number of equations are 3 and rank of A is less than 3, so unique solution is not possible, and in fact this system will have infinitely many solutions. So, nullity is 1 here, rank is equal to 2. So, there are solutions possible, and the third variable can you can assign arbitrary value to third variable, and still this will be, the third equation will be satisfied. So, what we can do is we can consider the system as 2x plus 0y plus 4z is equal to 4, and then we have 0x plus y plus 1 by 3z is equal to minus 1. Z, you can assign arbitrary values to z, this equation will still be satisfied. So, we can say x is equal to 4 minus 4z, and from here we can say y is equal to minus y minus 1 by minus 1 minus 1 by 3 z. So, you can assign different values to z and you will get different solutions, and that is why we say that infinitely many solutions are possible. So, with this we have come to an end of this lecture. In this lecture I have started with the basic concept of rank, and then we have discussed nullity, we have discussed column space, we have discussed how to find the column rank and row rank, we have discussed number of results, row rank is equal to column rank is equal to rank of the matrix. Then we have tried to relate this with the system of equations, when the system, what should be the rank of the given system of equations, so that we can have a unique solution, we may have infinitely many solutions possible. So, on the basis of this one can see when the solution will have, when the system of equations will have a unique solution, when it will have infinitely many solutions, or when the solution is not possible. That is it. Thank you.
Thank you.